Welcome to the future.
Welcome to the Muxall Open Internet of Things video blog. I am your host, Michael Crane. Okay, so let's take a closer look at some of the components I've come up with for our new controller. And we might as well start with the LCD. It is here's a better look at it. So, like I said, I want it as big as possible. Well, within reason, it needs to be able to, fit the keypad in it, right? So we want the LCD as big as possible, and we're going to, just where it displays the, so this will be like the chamber temp. This right here will be the target temp. This 180 down here. And that'll be in the status, and you can scroll to config and change some of the configs. And profile 1 is where you can set your profiles and your smoke mode, ending control, just like in the GUI, except you'll be able to set it through this. And this is the actual size. This is to scale. I don't know how much I'm zoomed in here, but this is probably what it. This probably doesn't make sense if you're watching this on a TV set versus looking at it through an iPhone. But anyway, this should be big enough to read at quite a distance away. So you'll be able to see at least what temperature the barbecue is currently set at a glance, what profile it's on, and that sort of thing. And like I said, it's transflective. I looked at the electronic paper displays, and I could not find one that was anywhere close to this size. They're either super big or super small. And then I also read that they're kind of funny about getting hit by direct sunlight, which I found kind of odd since they're put on a bunch of iReader type devices. But anyway, this transflective one should be nice, and plus it also has a backlight, which the iPaper ones, wouldn't. You'd have to basically shine a flashlight on it or have an external light shining on it. And this is this display I found is a New Haven display. It's a chip on glass. It's 160 by 100. It's transflective, solid white LED with backlight. FSTN positive. I'm not exactly sure what that means. And at the 6 o'clock optimal view is not right for the barbecue because we need a 12 o'clock optimal view, but I could not find one without special ordering one. So for this first prototype, we'll just live with this. It should be all right. When we go to build our production unit, we'll have to change this to 12 o'clock optimal view, and it supports a wide temperature range. Okay, and I don't really know if there's much we want to look at in here. So that's pretty much it. Oh yeah, the other thing is it's I2C interface, so I'm not going to be driving with the SPI. It'll be I2C. So I don't really know how to start to continue on. So let's I'll just do the best I can. All right. The next thing I want to look at is I guess we'll just jump to the schematic, since that's the only other way to show you the rest of the components. Since I don't have a PCB, this is still in design mode, right? So we're going to start on the high voltage tab, and if this looks familiar, it should. This is basically the same layout as what was in the trigger controller for the triacs. I've changed some of the actual, this ST triac is almost exactly the same as the triggers triac. It's a STA12, except this is surface mount, and this is a snubberless triac. Even though I kept the snubber circuit, for noise and that sort of thing. This is the new one that I spec'd out is snubberless. So, and we'll look at that here in a second. This circuit here's the same, except I changed some of the values here based on like this R12 right here was 47 ohms, was suggested by an ST app note that I read. Actually, we both read it, or we all read it in one of the videos. And I left this the 270 ohm just as a starting point. And that same app note also suggested a resistor here to help, with the to protect the gate on the ST triac, but it didn't specify really any way of. It didn't say how to size it, and it really didn't say much. It didn't even give a suggested value, so I just plugged a 270 in there, and we'll go from there. And if it causes us any problems, I can just leave it out, which is the nice part about that. And we'll look at the specs of these things here in a minute. We've got the opto-traic right here, which is, I did change that. This is a Vishay opto-traic. Let me see if I can find the spec sheet for that. Here we go. And it's just basically it's basically a zero crossing opto-traic. So what we had is what was in the original Traeger. It does support 120 and 240 volts. Actually, it supports 380 volts AC line. It's basically has similar specs as the other one. The other one, I forget the brand name of it, but I thought the Vishay was a little better, and so I decided to use the Vishay. Okay, and you can read through the specs here. It's what model is it? We got the VOT8026AB. So this guy right here, if you want to go look it up, and like I said, it had basically the same specs as the previous one. So I'm not going to go over it again. We might in another video. If people are interested in seeing some of the values or more of the specs on it. Okay, and then, of course, this ST triac is almost exactly the same, except it's a snubberless versus a snubber. The other one wasn't snubberless. At least I don't think it was a snubberless. So we don't need to look at the specs on that. These caps are interesting to look at. Let's take a look at that. These babies here, check these things out. These are AC line rated ceramic disc capacitors, of course, made by Vishay. All the best stuff's made by Vishay. Class X1 and Class Y1. Yeah, that's industrial grade, right? And these babies are the duck's guts right here of high voltage caps. These things just have boatloads of compliance certificates, and they're nice, and they're very expensive, by the way. I think they're about $3.50 each for a capacitor. Yeah, they have a 20 nanofarad, which is one of the things that I like, because in the original Traeger, they only had 10 nanofarads in here, and both the Art of Electronics guys had suggested they wanted a 50 nanofarad cap up here with a 100 ohm resistor, but the ST Micro spec'd out like 22 nanofarads here for this cap, so I thought that would be a good fit. So that's why I liked them, and I'm not going to stick a second cap in here to get it up to 40 nanofarads. I don't think it's necessary. In fact, I don't know if this whole circuit right here is necessary with a snubberless triac, except for it might help with the EMI noise a little bit. I don't know. We might try measuring that. This is going to add a little bit of cost. Okay. Oh, another thing I wanted to show you were these resistors. These are, and these are kind of funny. These are MELF resistors, and I just couldn't resist. Pardon the pun. Using these MELFs right here. They support like up to 200 volts or something like that's the operating. I think they support higher than that. I do believe. But I just couldn't resist. I used it again. Anyway, using the MELFs, right? These things are cool. Yeah, so I'm gonna put all MELFs in these high voltage, this high voltage section right here. So that'll be cool. Anyway, yeah. So they support high power. They're nice, and we can take closer. So that's automotive. I think that's AEC. Got good stability, pulse load, intrinsic sulfur resistance. Yeah, these things are pretty nice. The 204 is kind of weird. It's actually a 1208 package or something like that. I forget the equivalent of it is. But they're almost a half watt. And it says 200 volts, of course. I thought they were higher than that. Anyway, so there you go. Okay, so another thing I thought we should look at. This is it's just a little NPN transistor right here. And this doesn't need, it only needs like 20 milliamps. I think it only needs like 5 milliamps to get it turned on. But when I was looking at the spec sheet for this opto-traic, let's see if I can pull it up again here real quick. Yeah, so it says it only needs like 1.2 volts to turn on, but it has a current of 20 milliamps, right? Even though if you go up here to the top, it says it'll turn on with 5 milliamps. So 5 milliamps would have been okay to run this little LED in there with, without this transistor right here. I didn't want to load down 20 milliamps is like max per pin. System on a chip, which we haven't looked at yet, device. I decided to go ahead and put this in here just to be safe, because I don't want to load it down. And if you'll notice, I've added, so we have the auger, the igniter, and the fan, and I've also added another one for a spare for future expansion, right? So that's kind of nice. All right. So anyway, it's basically the same thing as what was in the trigger controller, except I've kind of modified it a bit. The next thing we can look at, since we're looking at this, is we can look at the power supply for it. Now, if you remember from the previous, this is the trigger controller that we looked at when I did the video, and I was just kind of mapping this out. But, they had that big-ass transformer sitting right here, a full-wave rectifier, and then they went into the 7805 voltage regulator, right? And I looked at that for a bit, but whoops, I spoiled it. If you guys saw it, anyway, I looked at that for a bit, but I saw this thing. Let me get rid of some of this. There, that's better. Sorry about that. I looked at doing that, but then I found this module right here. This is a Meanwell MPM-10-5, which is a 5-volt power supply. This thing is not very expensive. It's $11.90, which is damn near the prices of what one of those transformers cost. And it's got EMI filter in it. It's got some other filters, and it's a little switching. It's a switching power supply, right? And it's got a little transformer built into it, full wave rectifier, protection diode on the output, which is nice. And it's got a feedback going into a opto isolator, so it's actually isolated between this left side, the high voltage side, and the low voltage side, which is good, even though it's in the same device. It's got PWM control for controlling the voltage regulator, and OLP is overload protection, all in an $11.90 device. And I thought, wow, that's sweet. I don't have to build any of this stuff. I can just plug it on the board. So, and it supports 120 and 240 volts. And I added a switch in here and the fuse, which was in the original trigger controller. Okay. So that's pretty nice there. Hopefully that'll work out well. Okay. So the next thing I want to look at, the front panel that we looked at earlier. So here are their capacitive touch buttons. They're basically just going to be solder pads. They're just copper pads. They're about 11 millimeters in diameter. I'm using let's see if I can pull it up here, a microchip 8-channel capacitive touch sensor to do the sensing on these, and this thing's pretty nice. Of course, it has 8 inputs, which is exactly the number we need. It's got, you can program the sensitivity. It automatically recalibrates, which is pretty nice. Supports 3 to 5 volts. And it has a power button, which is nice. That's one of those features where push and hold, like on your phone to get it to turn off. So that's pretty good. It has a press and hold feature for volume-like applications where, it'll speed up as you hold it. Yeah, we're gonna put in that rotary encoder for that. I don't really like stuff like that, but anyway, and it's got a bunch of other stuff: RF detection, filters, EMI blocker, ESD ratings, a bunch of other stuff. Oh, it's also I2C, which is nice, and it's pretty small. It's in a 3mm by 3. Oh, now we're using the 14-pin SOIC, right? Yeah, we don't want a QFN. So yeah, that's a pretty nice little device. So and we're going to be talking to it from our system, from a little micro using R2C, which you can see right here. It's going to be interrupt driven. So this thing supports an interrupt. So it detects a touch. It'll send a interrupt signal to the micro know that it needs to start listening. And I don't know, we might try some polling with this. We'll have to play with it. But anyway, I reserved a spot on the micro for the interrupt. And here's the schematic for the rotary encoder. This is just a standard rotary encoder. I'm not going to look at it. I have a spec sheet for it, but it's very non-interesting. So we'll just call it the rotary encoder. Here's a schematic for it. And it's got a little push button on it here. That's what that PB is for right here. And this is just the rotary encoder A and B ports. That's how I can tell which direction it's going, and the push button, of course. And then right here we have the panel lights. And so there's 6 panel lights. Basically, what's going to happen, or what I'm thinking about, is having LEDs on either side for each row on both sides. So there'll be LED here, here, and here, kind of shining this way, and one over here shining this way. And hopefully that'll be enough to light up the whole panel. It should be. And that's the panel. Or wait, here's what a lot of people have been waiting for, and that's the micro. You can see here it's the ESP32 Pico D4. According to Expressive, it's a system in package module, which is based on the ESP32 system on chip micro. And I'll try to explain all this without trying to confuse everyone, because it is kind of confusing. So let's pull up the data sheet for the SIP package first, okay? Okay, so I'll just read it to you real quick. The ESP32, there you go. The ESP32 Pico D4 is a system-in-package SIP module that is based on the ESP32, providing complete Wi-Fi and Bluetooth functionality. At the core is the ESP32 chip, which is a single 2.4 gigahertz Wi-Fi and Bluetooth combo chip designed with TSMC's 40 nanometer ultra-low power technology. So the ESP32 Pico D4 integrates all peripheral components seamlessly, including a crystal oscillator, flash, filter, capacitors, and RF matching links in one single package. Yes, it's a chip. I don't know why they don't call it a micro, but anyway, given that no other peripheral components are involved, module welding and testing is not required either. Well, as such, the ESP32 Pico D4 reduces the complexity of supply chain and improves control efficiency. Okay, a bunch of other marketing wank there. Okay, let's, so it's got Wi-Fi, yep. It supports Bluetooth, and I'm not going to read you all these specs. It's basically just 2.4 gigahertz Wi-Fi. Oh, yeah, here it is right there. Oops, this right here. The Bluetooth. And I don't see... Oh, yeah, it does support BLE, so that's good. And then it's got these module interfaces, and it's got an onboard ADC, a DAC, supports touch sensors, SD cards, SPI bus, EMAC, PWM. It's got a lead PWM. Not exactly sure what the difference between those are. I guess we can look at it later. UART, I2C, I2S, infrared, remote controller support, GPIOs, and pulse counter. It's even got an on-chip Hall sensor. right down here. It's got an integrated 40 megahertz crystal oscillator, integrated SPI flash of 4 megs. That's pretty nice. 3.3 volts. Operating current is 80 milliamps. That's Oh, here we go. Minimum current delivered by power supply needs to be 500 milliamps. And somewhere I read when I was sizing out the power supply, it can actually go up to 1100 milliamps. So that's why I sized it. The power supply is so large when we looked at that earlier. Anyway, it's got a bunch of other junk. So let's pull up the SP32 datasheet. And this is the system, the sock that's in the SIP. I hope you're following all this. There's going to be a test afterwards. Okay, we just want the details. Here we go. So here's all the Wi-Fi stuff. Yeah, 2.4 gigahertz. A bunch of other Wi-Fi junk in here. It's got 4 virtual Wi-Fi interfaces. Not exactly sure what that is. Okay, so here's the CPU and memory. It's got a, the one we have is a dual-core 32-bit LX microprocessor. 600 MIPS. So, yeah, that's pretty nice. It's got 448 kilobytes of ROM, 520 kilobytes of SRAM, 16 kilobytes SRAM in the RTC. And I think RTC is real-time controller or something like that, but don't hold me to that. This QSPI supports multiple flash. That's what's accessing that 4 megs of flash that we saw earlier. Or that's what's being used for the 4 megs of flash. And then it's got an internal oscillator, but we have a 40 megahertz in the SIP package. So, yeah, this is a little bit confusing, so you have to kind of just bear with me, all right? 2 timer groups and watchdog, okay? It's got 34 GPIOs. Here's the 12-bit ADC. And so that's pretty nice, right? But I did not use the ADC in the Pico. We'll just call it the Pico, because I didn't want to. This little guy is going to be serving up the GUI for the barbecue controller. And it's going to be running the Wi-Fi. It's going to be running the LCD, and it's going to be communicating with our other devices. So I didn't want to load this. I didn't want to load the GPIOs down with a bunch of power requirements for the... Well, I didn't want to load the GPIOs down. I also didn't want to... and since it's running the Wi-Fi, I want to make sure it's got plenty of power for the Wi-Fi. And I also didn't want to make it busy or keep it too busy trying to run the ADC and these internal touch sensors. That's why I went ahead and just used external ones. And so all it has to do is communicate with them using SPI and I2C. Okay. And you just got 2 I2S ports, or can support up to 2 I2S. And with SD cards, put an Ethernet interface on it if you want, motor PWM and lead PWM channels, and our Hall sensor. So, pretty sweet little chip, huh? So let's just go over to the schematic real quick, take a look at it. See how I've got it wired up, starting from the left over here. These pins that are showing not available are for the accessing the Pico's flash, the 4 mega flash. It's using the QSPI bus. Okay, then we've got the interrupt for the ADC, the reset pin for the ADC, this VSPI bus. And support, I believe, is 3 different SPI devices on it with 3 different chip selects. Here's the chip select 0 for the ADC. And we've got the PWM for the buzzer, which we haven't looked at yet. The backlight pin for the keypad and LCD. And then we've got the encoder inputs. Here's the interrupt for the capacitive touch. There's a push button. And then we have 1, 2, 3, 4 triac control pins. Okay. And here's the I2C clock and data pins. So now for the cherry on top. Are you ready for this? This is the most expensive part of this whole new controller. This is the most expensive single part, I should say, of this whole controller. Are you ready? Here it is. The LTC-2984 ADC. Look at that. Ta-da! This thing is a beast. So let's take a look at the spec sheet real quick. All right. LTC-2984, multi-sensor high accuracy digital temperature measurement system with EEPROM. Directly digitizes 2, 3, or 4-wire RTDs, thermocouples, thermistors, and diodes. On-chip EEPROM, 3 to 5 volts, 20 flexible inputs, automatic thermocouple cold junction compensation, built-in standard and user programmable coefficients for thermocouples, RTDs, and thermistors, measures negative thermocouple voltages, automatic burnout, short circuit and fault detection, buffered inputs, mains ripple rejection, includes a 15 ppm per degree C reference. And this thing is nice. Check this out. This is definitely the duck's guts right here. It measures a wide variety of temperature sensors and digitally outputs the results in degrees Fahrenheit or Celsius, a 0.1%, 0.1 degree C accuracy, and 0.001 degree C resolution. The 2984 can measure temperature of virtually all standard Type B, E, J, K, N, S, R, T, or custom thermocouples, automatically compensates for cold junction temperatures, linearizes the results, can measure temperatures with standard 2, 3, or 4-wire RTDs, thermistors, and diodes. It has 20 reconfigurable analog inputs. You can swap them around. It includes excitation current sources, fault detection, and blah, blah, blah. And here is the little example application. But what's even nicer about this thing is, here we go. Let's see if I can find it. And the first whack is right here. This is called the universal inputs. And this is just sweet right here. So this way, what this is showing you right here, we can read the caption. It's universal inputs allow common hardware sharing for thermocouples, diodes, thermistors, 3-wire RTDs, and 4-wire RTDs. I don't know why they didn't mention 2-wire RTDs, because it also supports that, but I guess they are running out of room. Yeah, so basically what you can do is you can, it takes, let's see, it takes 1, 2, 3, 4 channels plus, so it takes about 4 channels, and you can either put a thermocouple on it, a thermistor, 3-wire RTD, 4-wire RTD, and you can also put a 2-wire RTD. I'm not sure why it's not on here, but like I said, they're probably just running out of room. Since this thing's got 20 inputs, you can put 4 of these guys per chip. And that's what I've done. I've got 1, 2, 3, 4 universal inputs on our new temperature controller. Tell me that's not sweet. So now, if you want to put a thermocouple for the chamber probe, or 2-wire, 3-wire, 4-wire, thermistor, anything you want to use, you can just swap it out. It should work. That's the theory anyway. This has not been tested, so don't hold me to this. But anyway, the chip does have to be reconfigured. So like if let's say if UIP1 stands for Universal Input 1, let's say it had the standard 2-wire RTD for the chamber probe, and the input 2 had the, let's say a 4-wire PT100 for the meat probe. if you wanted to change this guy out to a thermocouple, this chip has to be reconfigured to support that. You can't just plug it in. It's not a plug-and-play type thing. So the software is going to have to support it. It'll be like a drop-down to change them. But what's nice about it is you don't have to change the hardware, right? So that's just super sweet. So now you're saying, man, that is nice. How much is that beast? Well, let's go take a look. And if we come down here and we type in EDC, there it is. Ta-da! $50. That's for one of them. That is that is one expensive chip. $50. But, it's that is super sweet. And we can look how it's wired here real quick. It's nothing real interesting. It's just basically wired. All the outputs are wired exactly like I showed you in the data sheet. It's got diodes right here to measure the cold junction temperature for cold junction temperature compensation. These sense resistors, this is a supply right here running through this 2K as a sense resistor, or I'm sorry, to sense the current, and that's how it calibrates itself to for 2 and 4 wire measurements, or for different measurements, I should say. And here's just a bunch of bypass caps, and so there's two different sense sources and 2 different cold junction compensation sources, and this is all the SPI interface down here. More bypass caps. So I also wanted to show you, let's see here. So here's a little circuit for the buzzer. This is for the alarms that we were talking about earlier. It says buzzer, it should beep, right? And it's like at 2400 hertz. 2400 hertz. And so it's just going to beep. And then here's the backlight circuitry. It's using a little MOSFET. And here's the LCD wiring. Nothing interesting here. It's just, this is for like a charge pump inside this LCD to boost up the contrast voltage, okay? I think we've looked at everything. Don't forget, you can support the Muxall Open IoT channel by donation using a credit card and PayPal, or by purchasing products at the Muxall store. Details and links are in the description under this video. Well, that's it for this video. If you like the video, give it a big thumbs up. That helps. And hit the subscribe button. That really helps. If you have any questions or comments, post them in the comments under this video. Thank you for watching, and I'll see you next time.